All right, hello everybody. Welcome. We're going to talk about CoreDNS today, so I hope you're in the right place. My name is John Belamaric. I'm with Google. And
my name is Yang. I'm working for CoreDNS.
Yeah. So you're probably a little bit familiar with CoreDNS, at least because most of you are here for Kubernetes. And CoreDNS is the default DNS server in Kubernetes. But it is more than that. It is a general purpose DNS server, pretty much everything but a recursive DNS server, although there's ways to make it that too. So it's an authoritative DNS server primarily, but it's it's a little different than your traditional bind type of thing because we are written in Go, which is a memory safe language. A lot of people had a lot of CVEs in bind, and so one of the reasons that CoreDNS exists is for that. But more interestingly, it exists because of the level of flexibility it offers. So it's really, really easy to build integrations of CoreDNS with other backends. So sure, we support zone files. Sure, we support Kubernetes as a backend, but it's super easy to build other support. And in a few minutes, Yong is going to show you how to do that. Essentially, it's just a few, obviously it depends on how complicated your backend is, but it's just a few lines of code in general. Today, because of it's so easy, we support a bunch of different backends with, as I said, file being the biggest one, zone files, and then Kubernetes. Actually, probably Kubernetes is more widely used than file, which means we back using the Kubernetes API. But you can also do back directly, be backed directly by like your cloud provider's DNS service. So essentially, we can provide a caching layer for those reading from their APIs rather than from their upstream DNS. As a community, we're there's 387 contributors, but actively, there's just a handful of people. It's a pretty small, friendly place. So if you are interested in this, and I'll go through in detail some recent things that contributors added that are pretty cool, but we're very welcoming as a project, and it's pretty easy to get involved. I think now I'll hand it off to Yang, who's going to talk a little bit about how you might extend it, and then I'll talk about, like I said, some new things that are in there, and then we'll leave some time for Q&A.
Okay, thanks, John, for introduction. So I'm going to walk through a demo plugin. You're going to say, what exactly is this plugin doing? This plugin is doing a very simple thing. This is actually one of the most requested features by the community. Many times people come to us and say, okay, I have a network. My network is like internal network, but I have a DNS server that's going to serve both internal network as well as the outside. I do want a way to differentiate those internal and external networks. So if it's internal, I'm going to return one IP address for DNS requests. And if it's external, I'm going to return another IP, which is pretty straightforward, right? Many people request that a lot of times. I'm going to show this how you can do that with Golang, because many people come to us and say, okay, can you make a plugin, or can you allow us to achieve this goal with some configuration files? But eventually, we have some debate about if it's worth the effort to write a plugin, because the plugin, the complexity of how exactly you're going to handle different configuration is going to be a little convoluted. So we say, okay, maybe we can show a plugin, write a plugin in Golang and see how easy that is. Actually, that one I think it took me 1 day to get this one done. Yes, and you probably can get everything done with less than 1 day, maybe a couple hours. Okay. So as you can see, this is how this plugin is going to serve your network DNS entries. You have an internal network that's going to start with 172, prefix of 172. You have external network that can be anything, and you have a CoreDNS server sitting on the edge, serving both inside and outside. If your network is going to receive a DNS query of the same name, and if it's the traffic is coming from the internal, you're going to return 1.1.1.1. This is a fake IP. Anyway, right, just to give you an example. And if it's external, you're going to return 8.8.8.8. Fairly straightforward. So how do we achieve this goal? So there are only 3 functions you need to implement. The first function is it's called init function. This init function is going to perform a one-time initialization and register the setup function with caddy. And the setup function is the second function you're going to handle. That is to pass a configuration file, because you do have some very minimal configuration to say what you want to pass. And it adds a handler, and it will be called once for each of the plugin in the core file, and that's it. You'll set up the plugin. But finally, how exactly your plugin is going to handle or process DNS requests, that's the key, right? It's also fairly straightforward. There's only one function called the serve DNS. This function will process the DNS request. After you receive the request, you can decide what to do. You can either reply back with a response, or if you say, this is not my domain, I don't know what to do with that, you can pass the request to the next chain of the plugin. So you just say, I don't know how to handle that. Someone else will take care of that, and that's it. I'm going to show the code, the whole code of how exactly this is being done. As you can see, the init function is straightforward. This is nothing, just a stop function to say this is a demo plugin with a server type of DNS. And the second function, that's a setup. The setup is going to pass the core file, but because this is a demo plugin, we don't have a lot of configurations. We just say, let's just pass the simple standard core file without anything. Okay, so that's several lines of code again. Now we move to the serve DNS, which is the key of this plugin. So how exactly are you going to do that? You take a state, which is going to be request. You'll get a state, and then with the state, you can get a name of the query. That's a queue name. Now you can decide what to do with that. In this function, as you can see, we are going to reply with either 1.1.1.1 or 8.8.8.8, depending on the IP address of the query, the source IP of a query, and that's it. As you can see, only 1, 2, 3, 4, 5, 6, 7, 8 lines of code. Of course, that's pretty much it. I actually added a print line function just to let us see how exactly this is going to play out. But if you try this one, you're going to see it fairly straightforward, and that's it. Like I said, I spent one day, but you probably can spend maybe like 20 minutes to get everything done, right? Okay. So now you say, okay, I have a plugin. How exactly am I supposed to configure that? Because we said this is a demo plugin, so you really don't have a lot of configuration. If it happens that you do need a lot of configurations, you may need to make a little complicated on the setup parser. But for now, it's just a demo plugin. You set up one line to say, I'm going to invoke a demo plugin. That's it, the core file. And that's it. Finally, you're going to say, how exactly am I going to build that? The building of the CoreDNS plugin is a little, I'm going to say it's a little convoluted, unfortunately. You have to configure the setup file of your CoreDNS. You add one line to say you are going to invoke this demo plugin. You also need to copy the source code. But there's some easier way to make it happen. If you copy this line, a little strange line with a Docker, you can just run this command, and it will build the binary. Once your source code is compiled, you're going to see a binary called CoreDNS on your local directory, and you can just run that. So that's pretty much it. We do have the code available in CoreDNS repo. That's github.com CoreDNS demo, and you can take a look. And the total line code is 80 lines. And that's it. Okay.
Thanks, Yong. Yeah, so you can see it's super easy to extend, which means we do have a bunch of external plugins. If you go to our website, you'll see a section for external plugins where people have built plugins. You can pull those in and build your own CoreDNS. A few little notes that we don't have in the deck, but probably should. They're statically compiled in. There's no dynamic loading of plugins. And two, the ordering of plugins is fixed in the request. What you put in your configuration file of how your plugins doesn't matter at all between plugins. Like within a plugin, if you have multiple directives for a plugin, the order might matter. But that means that if you want to change that ordering for some reason, you have to recompile. So there's some little gotchas, but otherwise it's super easy to extend. To give you an idea of some of the things that that have been going on lately, so we just released, I think 2 days ago, yesterday maybe, 1.12.1, and probably the key thing I want to call out in that is back in 1.11.4, so about 6 months ago, I think, we broke something in Kubernetes, which is the way the PTR records, which are the reverse DNS records, are created for different service endpoints. And so we reverted that change. So if you are using CoreDNS in your Kubernetes environment, and you're on a version before 1.11.4, you're going to want to skip all the way to 1.12.1 and not go anywhere in between. Just an FYI, a little warning there. But over the course of the last year or so, we've added a few different interesting plugins. One is the timeouts plugin, which just allows you to configure some more options, a bunch of changes to other plugins. But what I'm going to drill into next is the multisocket plugin, and I'll explain the problem this solves. So we've had a long-standing issue in CoreDNS where we sort of hit a limit, a QPS limit, when no matter how much more CPU you give to CoreDNS, you can't get more QPS out of it. In fact, as you can see on this little graph, your QPS starts to decline. And so we weren't sure what the bottleneck is. And as I mentioned, like, it's a friendly place. So we actually had a brand new contributor come in. This is now maybe about a year and a half ago, because this one took a while to figure out. But they came in and started asking questions, showing graphs, and trying to figure out what was going on. And a couple other even new contributors jumped in. And over the course of a few months, we noticed a few things. And I'm going to show a little bit of the internal structure of CoreDNS to show how kind of this evolved. Internally, right, we have a thing we call a server, and it's what handles a given port. So when in your core file, this basically corresponds to one stanza that's got a port, a domain and a port, and that one server object basically has a routine that's pulling requests, off the UDP socket or whatever it may be, and then it's doling them out to Go routines, and dispatches them to Go routines, and then the actual resolution chain. So I guess maybe we didn't say it earlier, but when we talk about plugins, the way the DNS resolutions happens in CoreDNS is we have this list of plugins. They're either enabled or disabled based upon what's in the core file. And when we get a request, we just hand it to the first one in the chain. And then it calls the next plugin, which calls the next plugin, which calls the next plugin, which allows and then there's a reverse, right? As they return, you get another opportunity to affect the request. So this is this plugin chain. Depending on what plugins you have enabled, that could be very fast or very slow. And so, in order to, parallelize the requests, the server picks the requests off, dispatches them in Go routines, so in parallel running execution threads, effectively, and lets them all operate concurrently. So this is where we're hitting. This is the sort of internal structure, and where we're hitting the QPS limit. And so during all this experimentation, somebody said, well, let's see what happens if we create two servers. Because we can do this without even changing code. We can just do this in the configuration file. And so they just opened up another socket and just duplicated their environments and then just sprayed traffic across both of those ports, and lo and behold, the throughput doubled. And so it became clear that the bottleneck was in that the server couldn't pull things off of out of the socket fast enough and dispatch them fast enough to get a better QPS than what we had. So what we decided to do is the next experiment was, okay, if you use the SO reuse port, which is a sort of kernel feature that lets multiple sockets be attached to that same port, you can, internally, you can serve things still off the same port 53, but you can do it with multiple sockets. The kernel will distribute the packets across those different sockets for you. You don't need to do anything. It's actually super simple on the internal side too. And so that's what we implemented. And then what we found was that the number of sockets that we have really corresponds best to the sort of simplest default is just for every processor you have, for every CPU you have, create one socket. And when we did, and so we use this if you're familiar with Go limits its concurrency based on an environment variable, but Uber has this Go module you can pull in, which automatically, in a containerized environment, sets that appropriately. So we pulled that in, and I can show you, this was the result, of course, with the single-threaded environment. And then with 2 sockets, you can see that all the way up through 5 CPUs, we're seeing basically linear path with growth of QPS. 3 sockets, 4 sockets, 5 sockets. So really, we get now really good vertical scaling as long as you configure the multi-sockets appropriately. You can scale to as many CPUs as you want, and you get basically linear QPS scaling until you hit other limits, right? So I think if you figure it's 512 bytes per UDP packet, you saturate a 1 gig NIC at around 250K QPS maybe. Most likely, if you're running in a cloud environment, they're going to cap you before that anyway. So those are the kind of limits you start having to worry about. So this was released in 1.12. It requires SO reuse port, so this is not on by default because it might not be there in your kernel, or you might need some configuration to make that happen. But it's all you need to do to enable it is put multi-socket in your config file, and it will automatically adjust based upon the number of cores you give to that container, and you should see better performance. So that's really all we had to discuss, other than Q&A. So please come join us at CoreDNS. It's super, like I said, super friendly, small world, and easy to become a really make a significant impact. Any questions? Yes, sir.
So one of the biggest problems with CoreDNS is the scaling. Currently, CoreDNS is scaled based on the number of nodes in the cluster.
Little amplification.
Thank you. So currently, the main problem with CoreDNS is the scaling, because CoreDNS is scaled based on the number of nodes and not by the number of requests. Is there any planning on changing it?
So that's a great question. That's a great question. Actually, I was thinking about this last night. We should maybe add a slide on this. But so our current sort of default recommendation is using cluster proportional autoscaler, which is not really a very good recommendation, especially now that we have this better vertical scaling. So, I guess it's more about the recommendation at this point. Definitely, you'd be better off looking at, say, CPU utilization, especially with this configuration now. You also, frankly, probably can get away with. So one of the big problems we see repeatedly is early in Kubernetes life, a decision was made to to make it easy for developers as they're developing to like feed in a DNS request for a service that's like just the service name, right? And if the service is in your same namespace, then you just need that name, and you can kind of allows you an indirection where you can move that service around and your manifest doesn't have to change or whatever. But what that led to is this we call the ndots problem, where the way DNS resolution works is on the client side in the resolve.com file. So this is before CoreDNS is involved at all. There's a configuration option called ndots, and there's a search path. And basically any query that has like fewer than ndots dots in the query and is not fully qualified, so it doesn't end in a dot, will go through that search path. So what does that mean? It means if you put foo and you feed that into your process as your service name, then the resolver on the client side will start trying names in that search path. And in Kubernetes, the search path is long. It's like first you try foo.service name, then or foo.namespace, and then you try like, or foo.namespace.svc, and then you right, and you end up basically any DNS name that's not fully qualified results in 6 queries before it hits the right one if it's for an external service, at least 6. If it's for, and depending on, if it's for an internal service, it's going to hit anywhere from 1 to 6, depending on if it's in a different namespace or whatever. So that's like an query amplification, and that has nothing to do with CoreDNS. That's about how Kubernetes configures the resolve.conf, but it leads to the scale problem that you're bringing up, because if you are doing a lot of queries for external services, your number of, like we see this with like, say, like buckets, right? And then, so the recommendations I would give you on the scale issue is first, if you can do it, most people can't, is make everybody put a fully qualified domain name. And when I say fully qualified, I don't mean ending in .com, I mean ending in .com dot, right? That last dot is the most critical piece because it tells it, don't use the search path. So that cuts immediately any external queries into 1/6 of what they would be otherwise. Most people can't enforce that easily. So in that case, I would say now that we have this multi-socket thing, just run 2 CoreDNSs and give them like, 8 CPUs or whatever, and for most people that's going to be fine. But otherwise, I'm going to suggest scaling based upon CPU utilization and do horizontally. So give it a bunch of, or a vertical pod autoscaler. I haven't thought it all through, but that would be my recommendation. The other scale factor, and I'm sorry, I'm going on long on this topic. The other limit you have to worry about is the number of services in your cluster, which directly affects the memory used by CoreDNS. So in your memory limits, if you have a lot of services or a lot of endpoints in headless services, then that's basically what the memory correlates to. Any other questions? Are we out of time? There's another question here. We still have a lot of time.
On that same topic, we're using node local DNS on our side to like kind of cache at the node level. Like how would you compare like that new capacity that you have now to vertical scale compared to node local DNS?
Great question. So node local DNS solves similar but also different problems, additional problems as well. I would recommend, in general, you do want to run node local DNS, but if you've got a lot of nodes, it's actually more expensive, right? You're using resources on every node. But the problems it solves is, one, it shortcuts any requests to like stub domains or external domains. I believe it does external domains too. And it will look those up directly and cache them. The other big thing it does is we had this problem in the high scale environments where, so internally the kernel has a connection tracking table, and it's got a limited number of slots. And if you make a TCP connection and then you close the TCP connection, there's a close, there's disconnects, and so it removes the entry. But UDP connections don't, because they're connectionless. It doesn't know when to remove the entry from the table, so it lets them time out. So when that entry, when you're it's like 75 seconds or some really long time period. So if you have a lot of queries going out, you fill up that connection table and you start like literally dropping packets, right? So you see failures in your resolution at that point. So Node Local DNS fixes that because it turns off connection tracking for those UDP connections going out for DNS, and it actually upgrades connections to the upstream CoreDNS to use TCP instead. So Node Local DNS is CoreDNS. It's just a special build of it with most of the features stripped out to make it smaller. But so I would recommend, yes, you use it. The only downsides that I can think of are, one, you have to run on every node. If you've got 50,000 nodes, well, most people don't have 50,000. If you've got 10,000, 5,000, that might be more expensive than running a few core DNSs. Two, the default TTL for services is 5 seconds. In a centralized core DNS, you can turn off DNS cache for those because we already have them in memory. I think we probably do in our recommendations. So you don't have a delay when pods come and go out of a service of 5 seconds, whereas if it's in a local cache, Node Local DNS cache will keep that. So that's not much of an issue, but there's a little issue there. And then it's a single point of failure on your node because we don't run 2 core DNS instances in Node Local DNS, just one. But it's only on that node, so it's scoped to the node, so that's not that bad either. Does that answer your question? Okay. Any other questions? We have 3.5 minutes, lots of time. Okay, well, we'll be right over here if you need us, and happy to answer any additional questions should you have them.